Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss application of first law of thermodynamics to various processes. Let's begin. First process, let cooling process. Here we consider in an adiabatic system, or that cooling process is carried out through that of adiabatic process. Adiabatic process. Adiabatic in the sense, in that of process the heat treated as constant. Here heat is constant, means throughout that of process the change in heat is 0, means the heat is constant throughout that of process. So how first law of thermodynamics helps in that of cooling process, let us discuss. Consider 1 mole of an ideal gas that enclosed in a cylinder. That cylinder is perfectly insulated walls. That cylinder is perfectly insulated walls. And bottom. This is the bottom portion of that of cylinder. Here that cylinder is fitted with a perfectly insulated, frictionless and weightless piston. That is a piston. That piston is perfectly insulated, frictionless and weightless. That piston. Here we consider 1 mole of ideal gas. 1 mole of ideal gas. Let the pressure of the gas, let pressure of a gas be P. Volume of the gas let V, and temperature of that gas let T. And let the piston moves upward and gas expands. Since no heat enters or leaves the system, why? That system is adiabatic. The total system is adiabatic in nature. It is an adiabatic expansion of that of gas. So let the change in temperature of that of gas, change in temperature of gas, that is dT, change in temperature of the gas. According to first law of thermodynamics, what we get? The amount of heat supplied to that of system that is used in change in internal energy plus work done. That work done against that of external pressure. dQ is the amount of heat supplied to that of gas, du is the increase in internal energy of that of gas, dW is the work done against that of external pressure. Since it is the adiabatic process, adiabatic process in the sense, here du change in the heat supply dq, the change in heat will be 0 as the process is adiabatic. So, we write here 0 is equal to du plus dw, dw is equal to pdv. So, we write 0 du plus pdv. Again, we know since Cv that is the specific heat of gas at constant volume. What is the specific heat of gas at constant volume? That is the amount of heat required to that of system. The amount of heat required to that of system to change, to raise the temperature of 1 gram of gas through 1 degree Kelvin, keeping the volume as constant, is known as specific heat of gas. Means the amount of heat required to raise the temperature of 1 gram of gas through 1 degree Kelvin at constant volume is known as the specific heat of gas at constant volume, and that is denoted as, that will be, what is, that is dq dt at constant volume, sorry, that not dq, that is du by dt, change in internal energy, that is du by dt at constant volume. So, here we can write in place of du, it will be Cv dt. So, let putting this in that of equation, we get du plus pdv is equal to 0. So, in place of du substitute Cv dt plus pdv is equal to 0, or Cv dt is equal to minus p dv, or dt will be minus p dv divided by Cv. Look at that of equation. This is the dt will be what? That is the change in temperature of gas. The negative sign indicates dt is negative. What is the significant sense? Since dt is negative, hence cooling is produced in an adiabatic process, okay. So, this is one of the application towards cooling process of first law of thermodynamics. Again, another application of first law of thermodynamics to another thermodynamic process. Let me take another thermodynamic process, melting process. And here we take the system or the process throughout that of isochoric process. Isochoric process. Isochoric in the sense here the volume is constant. Here the volume is constant, means the change of volume will be 0. Here let us consider mass small m of the substance. Let mass m of a substance gets converted into liquid on melting. The amount of substance which undergoes the melting process, that mass will be m, and let and the latent heat of fusion and latent heat of fusion of substance, let L, m be the mass of the substance and L be the latent, m is the mass of the substance and L be the latent heat of fusion of that of substance. What is latent heat of fusion? Means the substance, what is the latent heat of fusion of that substance? Means the heat required to change unit mass of substance into liquid at constant temperature. Okay, again I repeat, what is latent heat of fusion of that of substance? Means the amount of heat required to change unit mass of substance into liquid. Unit mass of the substance into liquid. What amount of heat is required at constant temperature is known as latent heat of fusion of that of substance. Here we take latent heat of fusion of the substance be L. Now according to our first of thermodynamics, what is the process? Let dq is the amount of heat given to that of substance. Then according to dq, and dq is the amount of heat given to the substance, So therefore according to first law of thermodynamics, the amount of heat supplied dq, that is used in change in internal energy plus work done against that of external pressure dw. But here the mass of the substance be m and latent heat of fusion of the substance be L. So here at equation 1, here again dq will be m into L. Let equation 2, from 1 and 2, from equation 1 and 2, that means ml is equal to du plus dw, or ml is equal to du plus dw, that is p dv, but here dv will be 0, since the process is isochoric in nature. The process is isochoric, so the volume was constant and the change in volume will be 0. That term will be 0, or ml is equal to du. Look here, the change in internal energy. du means the change in internal energy, that is same as that of ml. ml means the heat supplied to the system, that is ml. So what we signify from that equation? Hence during that of process, whole of the heat supplied to that of substance, hence during melting process, during melting process, whole of the heat, whole of the heat supplied, whole of the heat supplied to the substance is used in increasing the internal energy of the gas, in increasing the internal energy of the gas, internal energy of the gas. Okay. This is the melting process, how first law of thermodynamics helps to explain that of melting process. Then another application of first law of thermodynamics, boiling process. Third number of application, boiling process. Boiling process. Here we take the thermodynamic process as isobaric in nature, isobaric process. Isobaric in the sense, here pressure is constant, here pressure is constant, pressure is constant means change in pressure will be 0. Again, what is boiling? Boiling point or the process, boiling process, when a liquid is supplied heat, means we supply heat towards the liquid, what happens? It starts boiling at a particular temperature, call it boiling point. What happened in that of boiling point? At boiling point, the pressure is kept constant and unit mass of the liquid requires a definite amount of heat energy to change from liquid to vapor state. Okay, again I repeat, at boiling point we take pressure is constant, then unit mass of the liquid requires a definite amount of heat energy to change from liquid to vapor state. The amount of heat supplied is called that of latent heat of vaporization of that liquid, latent heat of vaporization of that of liquid, and the process is known as basically that boiling process. So we consider, let liquid of mass, let liquid of mass small m at a temperature equal to its boiling point, and latent heat of vaporization, latent heat of vaporization, let L, means the amount of heat required of unit mass of liquid requires a definite amount of heat energy to change from liquid to vapor state is known as the latent heat of vaporization, and the amount of heat supplied to convert that of whole liquid into vapor, that will be dq. So dq, the amount of heat required, that will be changed to m into L, that equation 1, as the latent heat of vaporization will be L, m is the mass of that of liquid, so dq will be ml. Then according to first law of thermodynamics, according to first law of thermodynamics, what we get? the amount of heat supplied dq will be du plus dw, that equation number 2. Now from 1 and 2, from equation 1 and 2, what we get? ml is equal to du plus dw, or ml is equal to du plus pdv, or du is equal to ml minus pdv, or du is equal to ml minus p. Change in volume is written as Vf minus Vi. Vf is the final volume, where Vf, that is final volume, and Vi, that is the initial volume. So the change in volume will be dV. That is the equation, change in volume ml minus p dV. So from that of equation we clarify, hence the heat supplied in boiling process is used in both increasing in internal energy and doing some external work. So hence heat supplied in boiling process is used in both increasing the internal energy and doing some external work, So here first law of thermodynamics helps to describe boiling process. Next, application number 4, the relation between Cp and Cv, which is known as the Mayer's formula, No, Cp is the specific heat of gas at constant pressure, here the specific heat of gas at constant volume. What is the relation in between these two? We take 1 mole of gas and a small amount of heat dq, that is supplied to that of gas. Let us take 1 mole of gas and small amount of heat, dq is given to that of gas, okay. Then according to first law of thermodynamics, what we have? According to first law of thermodynamics, what we get? dq is equal to du plus pdv, okay, where dq is the amount of heat supplied, then du is the increase in internal energy of the gas, and pdv is the work done against that of external pressure, that is dw, which is known as pdv. So first case 1, if we consider heat dq is supplied to the gas at constant volume, let its temperature increase by dt. So in case 1, if heat dq same heat dq is supplied to the gas at constant volume and let its temperature increases by dt, increases by what? By dt. So, the specific heat of gas at constant volume, so Cv, that is the specific heat of the gas at constant volume, will be what? dq by dt at constant volume, means dq amount of heat is supplied to that of gas and that change to the or to increase that of temperature to dt. So, the specific heat of gas at constant volume will be that much, then dq is equal to Cv dt. Since the volume of the gas remains constant, dV will be 0, change in volume will be 0. Now, putting this in that equation, since let that is equation number 1, that is equation number 2, therefore, putting 2 in 1, we get what? Cv dt is equal to du plus pdv, So, change in volume will be 0 here, since volume of the gas remains constant, dv is equal to 0, since volume of gas remains constant, dv term will be 0. So, du is equal to Cv dt, that means that term will be 0. So, du is equal to Cv dt, that equation number 3 here. This is happen for that of specific heat of gas at constant volume. Again, if we consider case number 2 here, case number 2 means that same amount of heat is supplied to that of gas at constant pressure. Then what happened? If heat dq is supplied to the gas at constant pressure, and let its temperature increases by dt, hence both the internal energy of the gas will be increased and the work done against that of pressure will be increased. Heat dq is supplied to that of constant pressure. So, the specific heat, therefore, specific heat of the gas at constant pressure will be dq by dt at constant pressure. Therefore, dq will be Cp dt. Now, equation number 4 here, let equation number 4 here. Now, putting that value in equation number 1, putting 4 in equation 1, what we get? Cp dt is equal to du plus pdv, Here Cp dt, du is equal to Cv dt, that from equation number 3, Cv dt plus pdv, we get here. Look here how I solve that one. Taking here as equation number 5. We know from gas equation, PV is equal to nRT, but we consider 1 gram mole of gas, so it will be PV is equal to RT. Now, differentiating both sides, differentiating at constant pressure. Let me differentiate both sides at constant pressure. Then what we have? We achieve P dV is equal to R dt. P dV is equal to R dt. Now putting the value of P dV in equation 5. Therefore we write here what is Cp dt is equal to Cv dt plus, in place of P dV we write R dt, or Cp minus Cv of dt is equal to R dt. dt cancel out from both sides. So Cp minus Cv is equal to R. Cp minus Cv is equal to R. That is the relation between Cp and Cv. Specific heat of gas at constant pressure and specific heat of gas at constant volume. R is the universal gas constant. So here you note that if we consider 1 gram mole of gas, 1 mole of gas, then in always it carried out the ratio of Cp by Cv is equal to always a constant. Value will be gamma. Cp by Cv is always a constant for what? For 1 mole of gas. 1 mole of gas, that will be always a constant. This is the relation between Cp and Cv. First case we consider same amount of heat is supplied for that of specific heat of gas at constant volume. Here the specific heat of gas at constant pressure. Combining these two and we consider the gas equation. So finally we prove Cp minus Cv is equal to R. So with the help of this video lecture we understand what are the applications of first law of thermodynamics through various processes. We consider cooling process in adiabatic system. We get the result. Then for melting process in that of isochoric system, we get that of result. Then the boiling process in that of isobaric process, in that of isobaric system, we get the result. And finally relation between Cp and Cv, which is known as the Mayer's formula. Cp, that is the specific heat of gas at constant pressure, and Cv, specific heat of gas at constant volume. Finally we derive the relation as Cp minus Cv is equal to R and Cp by Cv is equal to gamma for 1 mole of gas, that is always a constant value. So with this useful and informative notes, let me wind up this session. Thank you.